Perovskite solar cells are a new cutting-edge technology that has the whole renewable energy industry excited because of this little red and yellow line. The first perovskite solar cell was published in a paper in 2009, achieving a cell efficiency of 3.8%. Since then, the technology has been advancing rapidly, with the most recent record efficiency for single-junction cells being 23.3%. Even greater efficiencies can be achieved by using perovskites in tandem with other semiconductors with different band gaps to capture more of the electromagnetic spectrum. Researchers at the ENGN have achieved record efficiencies for perovskite silicon and perovskite SiGe tandem cells with respective efficiencies of 26.4% and 23.9%. Perovskite solar cells have several advantages over traditional silicon solar cells. They have a high absorption coefficient, meaning they require less material to absorb light. This means that they can be used to make thin, lightweight, and potentially flexible solar cells. The fabrication process is relatively simple as well compared to silicon. The most promising method, called solvent-solvent extraction, or SSE, as shown in this picture, uses a secondary solvent instead of high temperatures to encourage the growth of crystals and remove the initial solvent. This method allows uniform control over the shape and size of perovskites formed. It's more commercially viable as it does not require heat treatment and occurs at a faster rate than other methods. A perovskite is the name given to any crystal with the structure of atoms ABX3. This crystal structure, in turn, is named after the naturally occurring mineral calcium titanate, known as perovskite. Unlike the natural calcium titanate, researchers have discovered that hybrid metal organic halide crystals behave like a semiconductor and can be used to build solar cells. Here's the formula fitting this structure that's currently being researched. However, as late as this past April, researchers are still writing that the working principles of perovskite solar cells are not fully understood. As best as we can tell, when the perovskite lattice is struck by a photon above its band gap, it creates a loosely bound state known as an exciton, which is able to diffuse through the lattice. The inherent thermal voltage is actually enough to dissociate the exciton into an electron and a hole, and the semiconductor proceeds to generate photovoltage and photocurrent in a similar way to a silicon solar cell, with electrons and holes collecting at selective contacts before traveling around the circuit. The key challenges that PSCs are facing are instability, lead toxicity, and upscaling of the manufacturing process. The stability of perovskite devices must be addressed to achieve commercialization. This picture shows a fresh perovskite solar film on the left and a degraded film exposed to dry air and light for just 6 days on the right. Traditional silicon solar cells have an average degradation rate of 0.5% per year, which is often ensured for 25 years under operational conditions. For perovskite solar cells to compete within the PV market, they must reach similar levels of stability under working conditions. Judging from the recent explosive growth in efficiency and research popularity, these low-cost photovoltaic cells are expected to be a breakthrough. If these challenges can be overcome, perovskite solar cell technology could be a promising alternative or addition to silicon because it has the potential to create low-cost, high-efficiency solar cells.